In the previous recording, you will have this part. So here, in this note number 1, we know the energy of the stimulating photon and the emitted photon has to be similar. So energy of this photon and energy of this stimulated photon and emitted photon, both of them are equal. We know the energy of a photon can be given by HF, and it is also equal to E1 minus E2. So that is how we got this first equation. And the second equation is second note, both photons are in same phase, frequency and direction of travel. So as I mentioned earlier, if all of these characters match, then we call them as coherent. And this phenomenon was predicted by Einstein. Okay. So now we have understood the basic 3 processes that could occur when light interacts with a certain medium. So let's see how laser uses these 3 processes to amplify the light. So subtopic laser action. So under that, let's write down in laser, it is arranged such that in laser, it is arranged such that the emission of photons due to stimulated emission is laser is arranged such that the emission of photons due to stimulated emission exceeds the emission, the spontaneous emission. So in laser, we are trying to get coherent light. The light all has similar direction and similar frequency and everything. So which light will give us this character, coherent or incoherent? Obviously, it's the coherent. So if you want to have coherent light, then we have to have more stimulated emission than spontaneous emission. So in laser, it is arranged so the stimulated emission exceeds the spontaneous emission. Okay. Note number 2, the second point. Why do we need to increase the stimulated emission? The reason is usually in a medium, when light is traveling through, what happens to the intensity of light? It will reduce, right? And when this is very thick, let's say a translucent medium, when you're looking at the light from this side, the intensity will reduce, right? The brightness would have reduced. But in a laser, we want the opposite to happen. We want, when light passes through, we want its intensity to increase. We want the intensity to increase. So if we want the intensity to increase, then as these photons move through, it has to produce more photons. Then only the light's intensity will increase. Okay. So that is the reason that we try to exceed the stimulated emission above spontaneous emission. So second point, that is to increase the intensity, that is to increase the intensity, increase the intensity as it passes, as it passes through the medium, through the medium, rather than to decrease as usual. Next point. So if we want more stimulated emission, I want to have more excited electrons, right? If I want more stimulated emission, I want to have more excited electrons. So what is the general case? In the general case, there is more electrons. More electrons will be in the ground state. In most of the atoms, the electrons will be in the ground state. So if I draw all the electrons in a state, energy level, all the electrons will be in the ground state. But for the stimulation, for the stimulated emission to occur, we need to have the electron in the excited state. We want more electron in the excited state. So this is opposite to normal affairs, right? Normally it is in the ground state, but we need to have it in the excited state. So this is opposite to normal. Therefore, they call this setup as inverted population. This is inverted population. Usually the population is in the ground state, but here in a laser, it is in the excited state. Therefore, we call it as inverted population. So let's write down the point. This could be achieved by, this could be achieved by, populating more electrons in the excited state. In the excited state, which is opposite to normal affairs. To the normal affairs. This is known as inverted population. This is known as inverted population. If you want to have more spontaneous stimulated emission, we have to do this. And when this is done, we call that one as inverted population. So how we can set up an inverted population? To set up an inverted population, initially our electrons will be in the ground state. Initially, the electrons will be in the ground state. To set up an inverted population, I need to excite these electrons first. I need to excite these electrons first. Then only the electrons will go to the excited state. Without providing energy, can I do this? No, right? I cannot do that. So what I do is I shine light, or I radiate. Now let's say this has energy E2, this one has energy E1. Then I use light. I use light, so that photon, energy of that photon will be E2 minus E1. But we know this is equal to HF. So the frequency of the photon or the frequency of the radiation is E1, sorry, E2 minus E1 over H. By applying a radiation of frequency, whose frequency is equal to this frequency, we can pump these electrons from ground state to excited state. Is that idea clear? This last point, is it clear? Okay. So now we were talking about setting up an inverted population. So what is an inverted population? Usually the electron is in the ground state, but in a laser, we try to keep the electron in the excited state. Without providing energy, can I bring this electron to excited state? No, right? Is that idea clear? We cannot do that. Without energy, we cannot bring the electron to excited state. So what we are going to do is we are going to give energy. We are going to give energy by photons, using photons. So energy from this photon, these electrons will absorb the energy from this photon and get excited. But when we were discussing about absorption, we studied something very important. That is, these electrons will absorb energy only if the energy matches correctly. Otherwise, it won't absorb. So, what has to be the energy of this photon? It has to be E2 minus E1. But from Planck, we have an equation for energy of a photon, HF. So frequency is equal, frequency of the radiation is E2 minus E1 over H. So when I radiate this material, the frequency of the radiation has to be equal to this. Got it? By providing radiation with this frequency, we can pump the electron to excited state. Clear? How about the others? Hana and Najima? So let's note it down. Inverted population can be set up by a method called optical pumping. Here the material is illuminated with light consisting of photons photons of frequency f, which is equal frequency equal to E2 minus E1 over H. Okay, and we call this frequency this frequency is also known as the pumping frequency. Let's write about the pumping frequency in the next note. Okay. But there's a problem here. Now, just think, this is the electron. This is the electron that you are going to optically pump. So you send a photon. So you radiate it with a photon, and this becomes pumped. This is optically pumped. Therefore, it gets excited and goes to a higher energy state. Now this is pumped and it is in a higher energy state. Okay, it absorbs the photon and it is in a higher energy state. Now let's say you have another atom here. You have another atom here and there's a photon in the ground state. You want to excite this electron to come to the excited state. Then only you can set up an inverted population, right? You want more photon in the excited state. So you provide light. Now this photon, when it is passing this excited electron, what will it do? So there is two possibilities. It could excite this, or what else could happen? Due to this photon, what else could happen? Can this undergo stimulated emission? Can this undergo stimulated emission? Yes or no? Do you get my point? Now I am using optical pumping. Okay. So this optical pumping initially pumped one electron to higher energy state. And here I have another electron to be excited. So there's another photon. So when this photon is passing this atom, so it cannot go straight away here, right? It has to pass certain atoms. So if this photon is passing this atom, what it can do is, before exciting this electron, it could stimulate this electron, right, to fall to a lower energy state. Is it clear? So this could undergo stimulated emission to release a photon. So Yeah, so there is two possibility. Okay, this electron might undergo stimulated emission, or this one might get excited. But which one has more chance? Stimulated emission has more chance. Therefore, setting up an inverted population using this method is not easy. Is that idea clear? So let's mention that in the next note, in the next point. Yeah, here, this is radiated externally. Okay, this is radiated externally. So, okay, Imla, I got your idea. You're thinking that stimulated emission will occur only if this falls due to stimulated emission, right? You're thinking stimulated emission will occur only if this photon is due to spontaneous emission. It is not that. If you have a photon, if you have a photon whose energy will match this energy, then it will undergo stimulated emission. Okay. In the previous case, uh, due to a spontaneous emission, a photon can be produced. That photon will stimulate the second electron. So there, the idea is if the photon's energy, if this photon energy matches this difference, then it will stimulate. Okay. So next point, but soon as population, soon as population of excited level starts to increase, of excited level starts to increase, the pumping radiation, the pumping radiation induces stimulated emission, induces stimulated emission from excited to ground state, excited to ground state. Okay, is that point clear? So now, this setup, we are not able to use as a laser. To overcome this problem, now what is the problem? When we are trying to set up an inverted population, it is also inducing the stimulated emission. Therefore, we are not able to set up a inverted population properly. So to overcome this problem, three-level system is used. To overcome, we can tell this is overcome. This is overcome by three-level system. By three-level system. So in a three-level system, this is what happens. We have the ground state. This is the ground state, and let's say the ground state energy is E1. And we have two excited states, which is very close. So this is ground state E1, and this is energy state E2, and this is E3. So this is the ground state. And this we call the metastable state. Metastable state. I provide frequency. Now I am providing frequency of radiation E3 minus E1 over H. So this photon has this amount of frequency. So what can you tell about the excitation process or the absorption process? To which level will this electron move? Will it go to this first level or to the second level? The electron will move to the second level. I mean here, let's say this is 1, 2, and 3. So this is 1 and 2. So it goes to the second level because energy matches this level. Okay, energy is matching the difference between these two levels. Therefore, we are pumping to this level, and from this level, the electron undergoes spontaneous emission. It undergoes spontaneous emission to fall to this metastable energy level. And from there, it will again fall back to this ground state. From there, it will fall back to ground state. Yeah, I said this is the second level, okay? So I mentioned E2 as the first level, E3 as the second level. So from ground level, using this frequency, it will go to the second level. From second level, by spontaneous emission, it comes to this first level or the metastable level. So from there, it will fall back to ground level, emitting a photon of frequency E2 minus E1 over H. So we call this one as the pumping radiation. This process is pumping. Yeah, I will. Okay. And this is spontaneous. And this is stimulated. So I will go through this once again, what is happening here. First, we are providing frequency of radiation. This is the radiation's frequency. So when I provide this amount of frequency, using this energy, E3 minus E1 energy, this electron can go to this level, because we know that always the electron will get excited where the energy gap matches it. Okay, so this energy is matching E3 minus E1. Therefore, this electron will move on. When I give this radiation, it will go to this level. First, is that point clear? During pumping, it will go to level E3, I mean energy level E3. Is that clear? After that, this level is not very stable. Okay, when we compare E3 and E2, E3 is very less stable, E2 is comparatively stable. Pumping means exciting. Pumping means exciting. Okay. So after exciting, it goes to this level. So from there, this level is less stable. This is more stable. Therefore, this electron will tend to be in a more stable level, right? Comparatively more stable. So it spontaneously falls to this level. Okay, now the electron is over here. Is that idea clear? It spontaneously falls to this level. Now, have we overcome the problem? Can the pumping radiation stimulate this electron? Can the pumping radiation stimulate this electron? Yes or no? This is the pumping radiation. Can it stimulate this electron?